Greetings Math 93. This video is for lesson 6.2.3, the standard normal distribution. We're essentially going to work through one problem that is very similar to the ones that you were looking at in class. However, we are going to streamline this one a little bit more. In class, if you look through the lesson, you notice that we were doing a lot of conversion from a data point, which we were labeling with the variable x, to a z-score, which obviously we were using the letter z to identify it that way. We don't always have to convert everything over to z-scores, especially since you have access to technology in the form of your calculator. So what I'm going to go ahead and do in this video is go through the streamlined form of answering these questions. So what I encourage you to do is have the lesson open and available to you. So we would be on page 13 of your lesson book, and I would also have your calculator handy as well. If you do have notes from class with regards to how to navigate the calculator, please have those ready in front of you as well. I will be describing what I am doing, but I do not have access in order to kind of pull up a picture of the keypad. All right, so let's begin. This is the first question from the Take It Home. So the length of time students needed in order to complete a statistics test followed a distribution that was approximately normal, so that seems important. So I'm going to just highlight that. And the fact that it is normal means that I should begin to be conjuring this image of a normal distribution. Okay, so there's my line of symmetry, which, as we note, is where both the median and the mean are. And hopefully this is somewhat intuitive because both the mean and the median are measures of center. So in this case, the normal distribution is perfectly symmetric. So we would expect to see our measures of center in that central position. The other tick marks that I'm going to include here are just going to be the first, second, and third standard deviations above and below the mean. The mean was 74. So I'm going to go ahead and highlight that, 74 minutes, and I'm going to write 74 in here. The standard deviation was 8 minutes. Recall also from our class, the mean is denoted with the Greek letter mu, and the standard deviation is denoted with the Greek letter sigma. So as I go through here, in order to fill out these tick marks that I have around the mean, since we know that the standard deviation is 8, I'm going to, for the tick values that are above the mean, so in other words to the right, I'm going to add 8 to everything. So our first one would be 82, then 90, then 98. So I'm just repeatedly adding 8 to each tick mark as I go. Likewise, for all the tick marks that are below the mean, or in this case to the left, I'm going to subtract. And we would get 66, 58, and 50. Alright, so here we go. We're going to start digging a little bit further into A. So all the information that we've read in the initial part of the narrative has been used to construct what our normal distribution would look like. What proportion, so this might be a little bit different from the wording that was used in class. So when you think of proportion, you might think of probability or percent. So we've been doing this all along. They just decided to use a different word. So I believe the way that we should look at this is what the intention was not to confuse us necessarily, but to basically expose us to more terminology and so that we are more well informed. So what proportion of students took more than 1 hour to complete the test? The other thing that we want to note here, again, they might be trying to be tricky, but again, we're too smart for that. Notice that they're giving you everything measured out in the units of hours. but if we went back up here, everything was in minutes. So I'm going to come over here and just convert this over to minutes. So this way I can come to my graph and I can locate 60. So again, I don't have to be fancy about this. I can say 60 looks like it's about here. So I'm setting this barrier line where I would expect to see 60 along the horizontal axis, and I'm extending that line all the way to the distribution line for the normal curve. So again, they want more than, so then you need to decide which way should I shade. I guess you could shave, depending on what you're doing this on. I don't know, that's a weird tangent. I'm gonna let that lie. So from here, what we're gonna go ahead and do is, because it's saying more than, I'm gonna wanna shade everything to the right. The reason being is, again, if you train your gaze to all the values on the horizontal axis, these values that we see here, they are all greater than 60 minutes. All right, so now let's go ahead and actually write this out as in our probability notation. So we know that a capital P represents probability, and we are interested in the proportion of students that took more than 1 hour to complete. So we usually use the variable x. It's an arbitrary choice, but I am going to make a note for myself down here that x is going to be the time students took to complete the exam. Just so I kind of have a reference to go back to, because it's not necessarily super clear if we went back and just read through the question. Sometimes you literally have to tell yourself or remind yourself, what does the variable x equal? So in this case, because we are saying more than, I might use greater than, the greater than symbol, and then 60 minutes in my case. I would avoid using 1, because again, your data values on your normal distribution are in minutes. So in this case, if you were writing p is greater than, or sorry, probability of x is greater than 1, your reader may read that as, what's the probability that x is greater than 1 minute? Okay. So again, it may not be super obvious to us what this value should be, because as we can see, the barrier line that we put in here is not sitting directly on one of our standard deviation markers. So in order to answer this question, we are going to use our calculator. If we recall, we would do second, the vars key, and then we would select normal CDF. And again, here I'll go ahead and list out the general information. So we're going to have our lower number, our upper number, our mean, and our standard deviation. This is the order that you would need to enter this in. Depending on the model of your TI calculator, it may provide it for you in a list already, and you just kind of have to answer a series of questions. So in this case, I'm going to go ahead and come back and use purple here so it'll stand out. I'm interested in the lower bound here, because this is where the shading would have started. So I would have a normal CDF on my calculator. I'm going to enter 60, because that's the lower value. And again, depending on the model of your calculator, you would need to use a comma to separate your values. The upper actually, it just keeps going. Because again, remember that the tail of your normal distribution does not actually close off on the horizontal axis. So I'm just going to use an obscenely large number here. And for my situation, let's just use 99,999. That's way bigger. It's way further out past this normal distribution. So I'm kind of guaranteeing that I'm not like kind of shortchanging myself when I'm entering this into my calculator. My mean, we indicated, was 74, and the standard deviation was 8. So bear with me for a moment. So again, just to reiterate, have your calculator in front of you. I'm about to talk through the process. I'm going to do second and vars, and then I'm going to be taken to a new screen where I'm going to select option 2, which is normal CDF. That's going to bring everything back to my home screen, or in some cases you will be then taken to the list where you will enter in the parameters. I'm going to do 60 for my lower bound, comma, 99,999, comma, 74 for my mean, comma, and 8. Close that off, and we end up getting 0.9599408865. Okay, so in this situation, what I would say is let's go ahead and maybe convert this to a percentage. So I know that working with my decimal point, I'm going to move back 2 spaces. So I might answer this probability as saying there is a 95.99% chance, and again I'm just choosing to round to the second decimal place in this situation, that a student took greater than 60 minutes to complete the exam. Okay, so let's keep going. So for part B, we're asked to answer the question, what is the probability that a student needed between 70 and 80 minutes to complete the test? So this time, again, once you have drawn out your normal curve, I would encourage you to kind of draw out one every time if it's not provided for you. And I would locate 70, and I'm going to kind of say that that's maybe somewhere around here. Again, it does not have to be super exact. 80, that's somewhere in here. And no one wants us to really eyeball this. I think that that would be kind of difficult to do, but we are interested in the area under this portion of the curve. All right, so again, what we can do, we're going to go to our calculator, as handy dandy as it is, and we're going to do a normal CDF. Okay. Again, if it hasn't been made clear in the past, we do a normal CDF because we are trying to find the probability or the area under the curve. So again, we are going to do our lower value. So I'm going to try to color code this for us. So my lower value, I'm going to extend this out, we said was 70. My upper value, so this time I literally do have a stopping point in my shading. That's going to be at 80. My mean is 74. And my standard deviation, again, essentially how far away from the mean, and again, this is also given to you in the narrative, the standard deviation was 8. So again, if we do second vars, we're going to select option 2, which is normal CDF. We will type in 70 for our lower, 80 for our upper, 74 for our mean, and 8 for our standard deviation. Go ahead and hit enter, and I get the following results. I'm going to get 0.464 8351884. So again, if I convert this over to its percentage form, then I would get 46.48%. To finish this off with the probability notation, admittedly I probably should have jotted it down before I started, we're looking at the probability that x is between 70 and 80, and we know that that's going to be 46.48%. Let's look at one more. So, part C. How long did it take the fastest 5% of the students to complete the test? So, in this case, what I want you to note here is that we kind of just have to guesstimate where the top 5% of the students are in this. So, if you remember your empirical rule, we remember what the percentages for each of these strips that I'm kind of drawing in is. So remember that this part was 34% and this part was 34%. Because they're symmetric, we're seeing that mirroring that's happening. Then we had 13.5%, 13.5%, then 2.35%, 2.35%, then 0.15%, and 0.15%. So my top 5%, I'm kind of wanting to look around in this area. So I'm going to say, so my top 5%, well, at this point I'm only at 2.5, so maybe I'm about here is probably roughly where the top 5% is. So if I shade that in, I'm interested to find out, essentially, what this barrier number is. So what is this x value here? One other thing to note, if this is 5%, allegedly, then what is all of this? Well, we know that the total area under the curve is 100%, if we're looking at it as a percentage, or 1 in its decimal form. So this must be 95%. Okay. We need this in order to do our calculator work. Okay. So in this case, because we are going the opposite way, they've provided you the probability. They're giving you the top 5%. This time you are asked to find the data value. We are going to use inverse norm in your calculator to help us find this. Okay, so again, inverse norm is where we are going to give the, basically, how do I want to write that? Here's where we're going to put the area to the left. Of the barrier you drew in. Followed by the mean, followed by the standard deviation. So we have 3 values that we're putting in this time. So in our case, we will do inverse norm. And again, I'll talk through how to do that on the calculator. The area to the left of the barrier, that would be this part, the 95%. We are going to place that in here as a decimal. The mean, well, that's still 74 in this example. And the standard deviation we had learned from our narrative is 8. So I have this noted down for myself. Here's how we would enter this into the calculator. Get ready, get excited, it's about to get crazy. Okay, so we're going to do second, and we're going to do vars. Again, that's the button that is next to the clear key. Then we are going to select option 3, where it reads inverse norm, or INVNORM. We're going to hit enter. And again, depending on the model of your calculator, you are either going to be taken back to your home screen, or you are going to be taken to a list where you're going to answer a series of questions. In either case, we will put 0.95 for our area that we are interested in, followed by 74 for our mean, and 8 for our standard deviation. When we hit enter, I end up getting a value of 87.15882901. So I would approximate this and say I get a value of about 87.2 minutes I want to use the context of the problem in order to give a full picture of my answer. So again, if you kind of come back here and look at the barrier, would you say that this is about 87.2? I'm kind of thinking, yeah, I'm closer to the 90 on this normal curve than I am to the 82. So I think that that's a good guesstimate. One other thing that I want you to note, okay, you can kind of check your work here. Okay, so if I were to, I'm just going to scoot this up, but I still want to keep my picture here. If I were to, say, for example, do a normal CDF, and I'm going to use a lower bound of the 87.2 that we just found, and I'm going to look at the values that are going to just keep going. So again, I'm going to use my ridiculously large, arbitrarily chosen 99,999 as my upper bound. The mean stays 74, and the standard deviation stays 8. So if I go second vars, option 2 to get that normal CDF, and then enter my data in, what I end up getting is 0.0494714509. Essentially, if I were to round this, say, to the second decimal place, this gives you 0.05, and then if you went ahead and converted that into its percentage form, we're at 5%. Well, we just checked our work, essentially, is what we had done here. So it's not a coincidence. Let me just drive this home once more. I know this video is a little bit long, but hopefully we're kind of getting a lot out of it. What if I instead wanted to know, let's say, the probability that my time that my students took their test is less than 87.2. I should have indicated that for this one, this is the probability that x is greater than 87.2. Well, in this situation then, I would do a normal CDF. And this time, if I'm looking at this, let me highlight this in red. Sorry, there's going to be a lot of writing on that normal curve. If I'm starting at that 87.2, but I'm interested in what's going on less than it, the lower bound ends up going off into the negative direction. So I'm just going to use a negative 99,999 as my lower bound. I'm going to get ridiculous. I just want to make sure I've covered everything. It's an insurance policy, essentially. Then my upper bound, again, my upper bound is starting at that 87.2. The mean is 74. And the standard deviation is 8. If we plug this in, so second vars, option 2 of normal CDF, and then placing those values in, so my lower, my upper, my mean, and my standard deviation, lo and behold, the area under that portion of the curve is 0.950528549 So if we converted that, say, let's round it first to 90.951, which then becomes 95.1%, well, that's, again, not a coincidence. So notice that the area above 87.2 was about 5%, and the area, in this case, below 87.2 was 95.1. The only other item that I want to call out is that you might be saying, but wait, 5% plus 95.1% is 100.1%. We shouldn't be able to add this up and get something over 100%. But again, think back to previous discussions in class. What might be happening here? Why did we go slightly over 100? And hopefully what you're saying is, well, we did round a lot of our work. So the 87.2 is a rounded value that we are calculating and working with. Not only that, we also rounded the final answers after we were doing our normal CDF checks. So I know this video was a little bit long, but I hope that it was helpful. If you do have questions, please come see me. Thanks.